When people talk about interstellar travel, sending humans to other star systems, they usually focus on the obvious challenges, the vast distances, the enormous energy requirements, the decades or centuries of travel time, keeping humans alive during the journey. These are all real problems, certainly. But there's another problem, one that's rarely discussed in popular accounts of space exploration that might be even more fundamental and difficult to solve: interstellar dust and debris. At the speeds required for practical interstellar travel, significant fractions of the speed of light, even tiny particles, become catastrophic threats. A speck of dust, smaller than a grain of sand, something you wouldn't even notice on Earth, becomes a kinetic weapon capable of punching through your spacecraft and killing everyone aboard. The interstellar medium, which seems empty from our everyday perspective, becomes a minefield of deadly projectiles when you're traveling at 10% or 20% of light speed. This isn't science fiction speculation or theoretical hand-waving. This is straightforward physics, confirmed by our observations of space, and it represents a potentially insurmountable barrier to the kind of fast interstellar travel that would make reaching other star systems feasible within human lifetimes. Let me walk you through why this problem is so severe, why it's so difficult to solve, and why it fundamentally challenges our dreams of becoming an interstellar civilization. Let's start with the basic physics of high-velocity impacts, because understanding the energies involved is crucial to grasping the severity of the problem. Kinetic energy, the energy of motion, is given by the formula E = half mv squared, where m is mass and v is velocity. Notice that the energy depends on the square of velocity. This means that if you double your speed, you quadruple the kinetic energy. If you increase speed by a factor of 10, you increase kinetic energy by a factor of 100. Now, the speed of light is about 300,000 kilometers per second. If you're traveling at 10% of light speed, which is considered a relatively modest target for interstellar travel, that would get you to the nearest star in about 40 years. You're moving at 30,000 kilometers per second. That's about 100 times faster than the fastest spacecraft we've ever built. At these velocities, the kinetic energy of even tiny particles becomes enormous. Let me give you some concrete numbers to make this visceral. Consider a particle with the mass of a single grain of sand, about 1 milligram or 10⁻⁶ kilograms. If your spacecraft hits this particle while traveling at 10% of light speed, the kinetic energy of the impact is approximately 450,000 joules. That's equivalent to the energy released by about 100 grams of TNT or a small hand grenade. A single grain of sand at 10% light speed has the kinetic energy of an explosive. And it's not just the energy that matters, it's the power, the rate at which that energy is delivered. The impact happens so fast that the energy is deposited in a tiny fraction of a second, creating enormous pressures and temperatures that can vaporize material, create shock waves, and punch holes through solid metal. Now scale this up. If you hit a particle the size of a pebble, say, 1 gram instead of 1 milligram at 10% light speed, the impact energy is 450 million joules, equivalent to about 100 kilograms of TNT. That's a small bomb. A pebble-sized piece of rock at these speeds would obliterate anything it hit. And if you hit something the size of a golf ball, about 45 grams, the impact energy would be equivalent to about 10 tons of TNT, roughly the yield of the smallest tactical nuclear weapons. At 20% light speed, the energies would be 4 times higher. At 50% light speed, sometimes proposed for very fast interstellar missions, they'd be 25 times higher. These aren't abstract calculations. This is what would actually happen if your spacecraft, traveling at relativistic speeds, collided with interstellar debris. And here's the crucial question: how much debris is actually out there? The interstellar medium is not perfectly empty. Space between the stars contains gas, mostly hydrogen, with some helium at very low densities, typically about 1 atom per cubic centimeter. That's an extraordinarily good vacuum by terrestrial standards, far better than anything we can create in laboratories on Earth, but it's not zero. More importantly, the interstellar medium also contains dust, small solid particles ranging from molecules up to grains the size of sand or larger. These dust grains are created by dying stars, supernova explosions, and collisions between larger objects. They're spread throughout the galaxy, though their density varies considerably depending on location. In the general interstellar medium, the space between star systems away from dense clouds, the dust density is roughly 1 grain per cubic kilometer. That might sound incredibly sparse. A cubic kilometer is a huge volume, a box 1,000 meters on each side. 1 grain per cubic kilometer seems negligible. But now consider your spacecraft traveling at 10% light speed, 30,000 kilometers per second. In 1 second, your spacecraft sweeps through a cylinder of space 30,000 kilometers long. If we assume your spacecraft has a cross-sectional area of, say, 100 square meters, a modest-sized spacecraft, then in 1 second you sweep through a volume of about 3,000 cubic kilometers. At 1 dust grain per cubic kilometer, that's about 3,000 dust grains per second hitting your spacecraft. Over the course of a 40-year journey to Alpha Centauri, you'd encounter roughly 4 trillion dust grain impacts. 4 trillion tiny explosions, each releasing the energy of a hand grenade or more, scattered across the surface of your spacecraft. Now, not all of these impacts would be catastrophic. Many would hit thick parts of the ship's structure or shielding and be absorbed without causing critical damage. But many others would hit vulnerable areas, sensors, antennae, solar panels, cooling systems, life support equipment, hull seams. Even if only a tiny fraction of impacts cause serious damage, you're looking at potentially billions of damaging impacts over the course of the journey. And this assumes you're traveling through relatively empty space. If you pass through a region with higher dust density, perhaps near a nebula or a region of recent star formation, the impact rate could be much higher. Some regions of space have dust densities hundreds or thousands of times higher than the general interstellar medium. Passing through such a region at high speed would be like flying through a sandstorm made of grenades. Moreover, we're not just talking about dust. There are also larger objects, pebbles, rocks, chunks of ice, fragments from asteroid collisions or planetary formation. These are much rarer than dust grains, but they exist. And hitting even a single pebble-sized object could be catastrophic. The distribution of these larger particles follows a power law. There are many more small particles than large ones, but the large ones do exist. Estimates suggest that in a journey to Alpha Centauri, a spacecraft might encounter several particles in the centimeter size range and possibly even 1 or more larger objects. Each of these would carry enough energy to potentially destroy the spacecraft. So we have a fundamental problem. To reach other star systems in reasonable time frames, we need to travel at significant fractions of light speed. But at those speeds, the interstellar medium, far from being empty, becomes a continuous barrage of high-energy impacts, any one of which could be fatal. How do we solve this? Let's examine the proposed solutions and why each one is problematic. The first and most obvious solution is shielding. If tiny particles are going to hit your spacecraft with enormous energy, build thick armor that can absorb the impacts without failing. This is how we protect spacecraft in Earth orbit from micrometeoroids. We use Whipple shields, multi-layer structures designed to break up and vaporize incoming particles before they reach critical components. But here's the problem. At interstellar velocities, the required shielding becomes impractically massive. Let me explain why. When a high-velocity particle hits a shield, it doesn't just bounce off or get stopped, it vaporizes, creating a cloud of plasma and shrapnel that spreads outward from the impact point. A good shield design uses multiple layers: an outer bumper layer that takes the initial impact and vaporizes the particle, a gap where the resulting plasma cloud expands and dissipates, and an inner wall that stops any remaining fragments. For this to work at interstellar velocities, you need several things. The bumper layer needs to be thick enough to completely vaporize the incoming particle. The gap needs to be wide enough for the plasma cloud to expand and cool before hitting the inner wall, and the inner wall needs to be thick enough to stop any fragments that make it through. Calculations suggest that to protect against dust grains at 10% light speed, you'd need a bumper layer several centimeters thick, a gap of perhaps a meter, and an inner wall of similar thickness to the bumper. And this entire shield structure needs to cover the entire forward-facing area of your spacecraft. Now calculate the mass. If your spacecraft has a forward cross-section of 100 square meters and you need shielding with a total mass of, say, 100 kilograms per square meter, conservative estimate for multi-layer shielding, that's 10,000 kilograms just for the forward shield. And you probably need some shielding on other surfaces too, because your trajectory won't be perfectly straight and particles approach from various angles. This might not sound insurmountable, 10 tons of shielding on a large spacecraft. But remember, we're trying to accelerate this spacecraft to 10% of light speed, which requires enormous energy. The rocket equation tells us that the fuel required increases exponentially with the mass of the spacecraft. Every kilogram of shielding requires additional fuel to accelerate it, which requires more fuel to accelerate that fuel, and so on. Moreover, 10 tons of shielding might protect against typical dust grains, but what about larger particles? To protect against centimeter-sized rocks, you'd need much thicker shielding, perhaps meters thick in places. The mass escalates to hundreds of tons or more. And to protect against the rare but possible larger objects, you'd need shielding so massive that the spacecraft becomes impractical to accelerate. There's a fundamental trade-off here. The thicker your shielding, the more massive your spacecraft, the harder it is to accelerate to high speeds, which means either more fuel, making it even more massive, or lower speeds, making the journey take longer. You can't solve the problem with shielding alone without making the spacecraft so heavy that you can't achieve the speeds necessary for practical interstellar travel. The second proposed solution is active deflection. Detect incoming particles and use lasers, magnetic fields, or other means to deflect or destroy them before they hit. This sounds like science fiction, but let's examine whether it could work. For active deflection to work, you need several capabilities. First, you need to detect incoming particles at long range, far enough ahead that you have time to react. This is extraordinarily difficult because dust grains are tiny and don't reflect much light. You'd need very sensitive sensors scanning a huge volume of space ahead of your spacecraft. Second, you need to identify which particles pose a threat and prioritize them. You can't deflect everything. There are too many particles. You need to focus on the most dangerous ones, which means determining size, trajectory, and impact likelihood on the fly. Third, you need a deflection mechanism that works quickly and precisely. If you're traveling at 10% light speed and detect a particle 1,000 kilometers ahead, which would be impressive detection range, you have only 1/30th of a second to deflect it before impact. That's not much time. Lasers are the most commonly proposed deflection mechanism. The idea is to vaporize part of the incoming particle, creating a jet of gas that pushes the particle off course. But the power requirements are daunting. You need to deliver enough energy to vaporize a significant fraction of the particle's mass in a tiny fraction of a second, and you'd need to do this potentially thousands of times per second for continuous protection. Calculations suggest you'd need laser power in the gigawatt range for effective deflection of dust grain-sized particles at 10% light speed. That's comparable to the output of a large power plant. And you'd need to power this continuously throughout the journey for decades. Where does this power come from? Nuclear reactors are the most plausible source, but they add mass, which brings us back to the problem of accelerating a massive spacecraft. Solar panels won't work once you're far from the sun. Fusion might work if we can develop compact fusion reactors, but that's still speculative technology. Moreover, there's a fundamental problem. You can't detect and deflect everything. Particles smaller than a certain size won't reflect enough light to detect at useful range. Particles approaching from certain angles might be in sensor blind spots. The sheer number of particles means some will get through. Active deflection could reduce the impact rate, perhaps significantly, but it can't eliminate it entirely. And active deflection doesn't help at all with larger objects, pebbles, rocks, chunks of ice. These are too massive to deflect with realistic laser power on short notice. If you're unlucky enough to be on a collision course with a centimeter-sized rock, active deflection won't save you. The third proposed solution is navigation. Plot a course that avoids regions of high dust density. If you can identify and avoid dusty regions of space, you reduce the number of impacts. This has some merit. We can map the distribution of interstellar dust to some extent using observations of how it absorbs and scatters light from background stars. We know that some regions are dustier than others. In principle, you could plan a route that threads through relatively empty regions, but there are severe limitations. First, our maps of interstellar dust distribution are incomplete and low resolution. We can identify large-scale structures, nebulae, dust clouds, regions near star-forming areas, but we can't map the distribution at fine scales. We can't tell you whether a particular cubic kilometer along your route has 1 dust grain or 10. Second, even the empty regions aren't truly empty. The general interstellar medium, far from any dense clouds, still contains about 1 dust grain per cubic kilometer. That's the baseline. You can avoid the worst regions, but you can't avoid all dust. Third, navigation constraints limit your options. The straightest path between 2 stars might pass through a dusty region, but going around might add decades or centuries to the journey. Is it worth adding 50 years to a trip to avoid a region that's only moderately dustier than average? The trade-offs are not obvious. Fourth, dust distribution can change on timescales shorter than interstellar journeys. Supernova explosions, stellar winds, shock waves from various astrophysical events, these can create new dust clouds or disperse existing ones. Your carefully planned route through empty space might encounter unexpected dust clouds that formed or moved during your decades-long journey, so navigation helps, but it doesn't solve the problem. It reduces risk, but doesn't eliminate it. The fourth proposed solution is redundancy and self-repair. Build spacecraft that can tolerate damage and repair themselves. Instead of trying to prevent all impacts, accept that impacts will occur and design the spacecraft to survive them. This makes sense to a degree. Any sensible interstellar spacecraft design would include redundancy in critical systems, modular design that compartmentalizes damage, and repair capabilities, either through onboard crew or robotic systems. But there are limits to what redundancy can achieve. If a pebble-sized rock punches through your spacecraft at 10% light speed, releasing the energy of a bomb, no amount of redundancy in that section helps. That section is simply destroyed. Redundancy means you have backup systems elsewhere, but it doesn't prevent the loss of whatever was in the impact zone. And if impacts are frequent, thousands per second of dust grains, plus occasional larger objects, the cumulative damage over decades becomes overwhelming. You can't repair damage faster than it occurs if impacts are happening constantly. The spacecraft slowly degrades, systems fail, and eventually critical damage accumulates. Moreover, self-repair requires carrying spare parts repair equipment, and either crew or sophisticated robots to do the repairs. All of this adds mass, which brings us back to the fundamental problem of accelerating a massive spacecraft to high speeds, so redundancy and self-repair are necessary but not sufficient. They can help a spacecraft survive some damage, but they can't compensate for the continuous battering of high-velocity impacts over a decades-long journey. Now, let me introduce the solution that's most commonly proposed by serious interstellar mission concepts. Don't send humans, send tiny, lightweight probes that can be accelerated to very high speeds with minimal mass. This is the approach of projects like Breakthrough Starshot, which proposes sending gram-scale probes accelerated by powerful lasers to 20% of light speed. The idea is that if the probe is small enough and light enough, you can accelerate it with ground-based lasers, and if it's damaged by impacts, you just send more probes, make them cheap and numerous rather than large and robust. This approach sidesteps many of the problems I've described. A gram-scale probe has minimal cross-sectional area, so it sweeps through less space and encounters fewer particles. It doesn't need life support, so it can be much simpler and more robust. It's fast, so the journey time is shorter and there's less total exposure to impacts. And if some fraction of probes are destroyed by impacts, you compensate by sending many probes rather than one large spacecraft. But notice what we've given up. We're not sending humans anymore. We're sending tiny robots that can take pictures and transmit data back, but can't establish colonies, can't explore in detail, can't adapt to unexpected situations. We've scaled down our ambitions from sending people to other star systems to taking snapshots of other star systems with disposable cameras. This might be the most we can realistically achieve with foreseeable technology, but it's a far cry from the Star Trek vision of interstellar civilization. And even these tiny probes face serious challenges, from interstellar dust. A significant fraction will be destroyed by impacts, and those that survive might have damaged sensors or communication systems. So where does this leave us? We have a fundamental problem. Interstellar space, while sparse by everyday standards, is dense enough to be extremely dangerous at the velocities required for practical interstellar travel. Shielding is too massive. Active deflection is too power-hungry. Navigation is too uncertain. Redundancy is insufficient. And miniaturization means giving up on crewed missions. Is there any solution I haven't mentioned? Are there any realistic approaches that could overcome this barrier? And what does this mean for humanity's long-term future? Are we truly confined to our solar system, not by energy constraints or distance, but by the impossibility of surviving the journey through the interstellar gauntlet? Let me explore some more exotic possibilities in part 2, because the conventional approaches don't seem to work, and if we're serious about interstellar travel, we need to think more radically. So we've established that conventional approaches to dealing with interstellar dust shielding, active deflection, navigation, redundancy, all have severe limitations that might make practical interstellar travel impossible, at least for crewed missions. Now I want to explore some more unconventional ideas, some more speculative approaches, and ultimately ask whether there are any realistic paths forward or whether we're genuinely trapped by this problem. Let's start with an idea that sounds like science fiction, but is actually based on real physics, using magnetic fields to deflect charged particles before they hit your spacecraft. The interstellar medium contains not just neutral dust, but also ionized gas particles that carry electric charge. If you could create a powerful magnetic field around your spacecraft, you could deflect these charged particles, pushing them around the ship rather than letting them impact it. This is actually how Earth's magnetosphere protects us from the solar wind. Charged particles from the sun are deflected by Earth's magnetic field. channeled toward the poles where they create auroras rather than striking the surface? Could we create an artificial magnetosphere around an interstellar spacecraft? The concept is sometimes called a magnetic sail or plasma magnet, and there have been serious proposals for using magnetic fields both for propulsion and for protection. The idea is to generate a strong magnetic field that extends far ahead of the spacecraft, perhaps thousands of kilometers, creating a bubble that deflects incoming charged particles. Here's the physics. A charged particle moving through a magnetic field experiences a Lorentz force that deflects its trajectory. If the magnetic field is strong enough and extends far enough, particles can be deflected around the spacecraft rather than impacting it. This works particularly well at high velocities because the faster the particle is moving, the stronger the deflection force for a given magnetic field strength. So what's the problem? Several problems, actually. First, not all interstellar dust is charged. Neutral particles and many dust grains are electrically neutral or only weakly charged, won't be deflected by magnetic fields at all. They'll sail right through your magnetic bubble and hit the spacecraft. So magnetic shielding only protects against a subset of the threat. Second, generating a magnetic field strong enough and large enough to deflect relativistic particles requires enormous power. The field strength needs to be intense, and it needs to extend over a large volume to provide sufficient deflection at the short timescales involved when you're traveling at 10% light speed. Rough calculations suggest you'd need magnetic field strengths of several Tesla, comparable to powerful laboratory magnets or MRI machines, extending over distances of thousands of kilometers. Generating this requires superconducting coils carrying enormous currents, which means massive infrastructure and significant power consumption. Third, maintaining superconducting coils in the space environment is challenging. Superconductors need to be kept at cryogenic temperatures, which requires cooling systems, which adds mass and complexity. Impacts from particles that do get through could damage the coils, potentially causing catastrophic failure of the magnetic field. Fourth, the magnetic field itself creates problems. Any charged particles you do deflect carry energy and momentum. They don't just disappear, they're pushed aside, and the force required to deflect them is transferred to your spacecraft. This creates drag, slowing you down. For an interstellar journey, this drag could be significant over decades of travel, requiring continuous thrust to maintain speed. Moreover, deflecting charged particles creates electromagnetic radiation, bremsstrahlung and synchrotron radiation, which could interfere with communications and sensors and could even pose a radiation hazard to crew or electronics. So magnetic shielding could help reduce the threat from charged particles, but it doesn't solve the fundamental problem. Neutral dust still gets through, the power and mass requirements are substantial, and the side effects create their own challenges. Another exotic idea, plasma shielding. Instead of using magnetic fields alone, surround your spacecraft with a cloud of plasma ionized gas that could absorb or deflect incoming particles before they reach the ship. The concept is to create a thick shell of plasma ahead of the spacecraft, perhaps by ionizing hydrogen with lasers or electron beams. Incoming dust grains would hit this plasma first, potentially being vaporized or slowed before reaching the spacecraft itself. This is even more speculative than magnetic shielding, and the problems are severe. First, you need to continuously generate and maintain the plasma cloud, which requires enormous power. You're essentially creating a small star atmosphere around your ship. Second, the plasma needs to be dense enough to stop or slow incoming particles, but if it's too dense, it creates its own drag, slowing your spacecraft. Third, maintaining the shape and position of a plasma cloud around a fast-moving spacecraft in the interstellar medium is extraordinarily difficult. The plasma wants to disperse and stream away. Fourth, the plasma itself emits radiation, thermal radiation, electromagnetic radiation from charged particle acceleration, which could interfere with observations and communications and could create a radiation hazard. Fifth, any impact between a dust grain and the plasma releases energy, creating heat and radiation that needs to be dissipated. If impacts are frequent, you're continuously dumping enormous amounts of energy into the plasma, which needs to be radiated away, or the plasma heats up uncontrollably. Some proposals have suggested combining magnetic and plasma shielding using magnetic fields to contain and shape a plasma cloud that provides the actual protection against impacts. This adds even more complexity and power requirements. Realistically, plasma shielding seems even more problematic than magnetic shielding, requiring technology and power levels far beyond current capabilities and facing fundamental physics challenges that might not be solvable. Now let me introduce a radically different approach. What if we don't try to stop the particles at all, but instead make the spacecraft so small and so strong that impacts don't matter? This is taking the breakthrough starshot idea to an extreme. Instead of a traditional spacecraft, imagine a solid object, perhaps a diamond crystal or a block of carbon nanotubes or some other ultra-strong material with all the essential functions miniaturized and embedded within it. Make it small enough that impacts are rare and strong enough that even when impacts occur, the structure survives. Diamond, for instance, is one of the hardest materials known. A dust grain impacting diamond at high velocity would create a tiny crater, releasing energy and possibly causing some local damage, but the bulk of the crystal would survive. If you made your entire spacecraft out of something like diamond with sensors and electronics embedded within the structure rather than on fragile external components, you might be able to survive impacts that would destroy a conventional spacecraft. But the problems are obvious. First, making complex electronics, sensors, communication systems, and power sources out of diamond or similar ultra-hard materials is far beyond current technology. We can make small diamond components, but a complete functional spacecraft? That's science fiction. Second, even diamond has limits. A sufficiently energetic impact will crack or shatter diamond. If you hit a large enough particle at high enough speed, the impact energy exceeds the material's ability to absorb it, and the structure fails catastrophically. Third, miniaturization has limits. To carry meaningful scientific instruments, to have enough power generation for communication across interstellar distances, to have computation capabilities for autonomous operation, all of this requires a minimum size and complexity. You can't shrink indefinitely without losing functionality. Fourth, even if you could build such a spacecraft, what's its purpose? If it's so small and so hardened that it can survive the journey, it probably can't do much when it arrives. It might survive to reach another star system, but can it conduct meaningful science? Can it communicate findings back to Earth? Can it do anything beyond just proving it's possible to get there? So extreme miniaturization and hardening might push the boundaries of survivability, but at the cost of functionality and with technology requirements that might be impossible to meet. Let me now consider the most radical idea of all. Maybe we don't send physical spacecraft at all. Maybe we send information. This gets into very speculative territory, but bear with me. If the goal of interstellar travel is to extend human presence to other star systems, one approach is to send the information needed to reconstruct human civilization, or even individual humans, at the destination. Imagine sending a tiny, heavily shielded probe carrying vast amounts of data, complete human genome sequences, digital libraries containing all of human knowledge, detailed plans for technology and infrastructure, even neural patterns or mind uploads if such technology becomes possible, This probe reaches another star system and uses local resources to build the machinery needed to decode the information and construct whatever it describes, perhaps growing humans from genetic templates, perhaps creating artificial intelligences based on human mind uploads, perhaps building robotic systems that then construct a human habitat and synthesize humans. This is essentially sending blueprints rather than physical objects, information rather than matter. The advantage is that information can be transmitted as signals, radio waves, or laser pulses that don't have mass and don't suffer from particle impacts the way physical objects do. You could send the same information via multiple redundant channels to ensure it gets through despite any interference. But the problems are formidable. First, this requires having robotic systems or automated manufacturing at the destination capable of building complex machinery from raw materials with no human supervision. This is far beyond current robotics and AI capabilities. We're talking about fully autonomous systems that can mine, refine, manufacture, and assemble complex technology on alien worlds. Second, if you're sending information to grow or create humans, you're creating people who have no connection to Earth, no direct experience of human civilization, possibly not even human childhoods. They'd be grown in artificial wombs or generated as adults. Are these really us extending to other star systems, or are they something else, a new branch of intelligence that happens to be derived from human templates? Third, the ethical questions are staggering. Is it ethical to create humans in isolation on distant worlds with no support system, no existing civilization, no choice about their circumstances? Is it ethical to create AI based on human minds and send them on one-way missions to interstellar destinations? Fourth, this doesn't help if the goal is for actual living humans to experience other star systems, to explore them, to establish colonies. Sending information and having it reconstructed at the destination is a very different thing from sending people. So information transmission might be a way to extend human influence or legacy to other star systems, but it's not the same as interstellar travel in the traditional sense, and it comes with its own profound challenges. Now, let me step back and consider the fundamental question. Given all these challenges, is crewed interstellar travel actually possible? Or are we fundamentally limited to our solar system by the barrier of interstellar dust? I think the honest answer is we don't know. But the challenges are so severe that crewed interstellar travel might indeed be impossible with any technology that obeys known physics. The problem isn't just one of engineering or resources, it's more fundamental. The interstellar medium, while sparse, is dense enough to be lethal at the velocities required for practical interstellar travel. And the solutions we can envision, shielding, deflection, miniaturization, all have limitations that might be insurmountable. Think about the energy budget. To accelerate a crewed spacecraft to 10% light speed requires enormous energy, perhaps equivalent to global civilization's energy consumption for weeks or months. To include adequate shielding and active deflection systems adds mass, requiring even more energy. To power the deflection systems during the journey requires continuous energy generation, probably nuclear, adding more mass. The mass spirals upward, the energy requirements become astronomical, and the mission becomes impractical. And even if we could solve the energy and mass problems, we still face the probabilistic threat of catastrophic impact with a larger particle. Even if our shields and deflection systems handle 99.9% of dust grains, that 0.1% that gets through, accumulated over trillions of impacts, could be devastating. And we can't predict or prevent collisions with rare but existing larger objects, the cosmic equivalent of a deer darting in front of your car, except the deer is a pebble moving at 10% light speed relative to you, and the impact releases the energy of tons of explosives. Moreover, faster speeds make the problem worse, not better. You might think, if impacts are the problem, let's just go faster and get there sooner, reducing total exposure time. But higher speeds mean higher impact energies, which means thicker shielding required, which means more mass, which makes it harder to achieve those higher speeds. And above certain velocities, perhaps 20% or 30% of light speed, the impact energies become so extreme that no conceivable shielding could protect against them. There might be a sweet spot velocity where you're fast enough to make the journey in reasonable time, but not so fast that impacts are unsurvivable. But that sweet spot might be at speeds perhaps 1% to 5% of light speed that make even nearby stars take centuries or millennia to reach. At those timescales, you're back to generation ships with all their attendant problems of maintaining a closed ecosystem and social cohesion over many lifetimes. So here's the sobering conclusion I am moving toward. Crude interstellar travel might be one of those things that sounds plausible, that doesn't violate any fundamental laws of physics, that we can imagine in principle, but that turns out to be practically impossible due to engineering constraints and environmental hazards. It's like traveling to the center of the Earth. Physically, there's no law preventing it. It's just rock and metal down there, nothing exotic. But the pressure, the temperature, the impossibility of maintaining a vehicle or tunnel at those conditions make it completely impractical. We'll never have people standing at Earth's core, not because of fundamental physics, but because of insurmountable engineering challenges. Similarly, we might never have people traveling between stars, not because it violates relativity or thermodynamics, but because the interstellar medium is too hazardous at the required velocities, and the engineering solutions are too massive, too power-hungry, too unreliable, or too speculative. Now, I can already hear the objections, but what about new technologies we haven't discovered yet? What about breakthroughs in materials science, in power generation, in shielding techniques? You're being too pessimistic, limiting yourself to current knowledge. And that's a fair point. Science and technology advance, sometimes in unexpected ways. Materials stronger than anything we currently have might be discovered. Power sources more efficient than nuclear fission or fusion might be developed. Shielding techniques we haven't thought of might emerge. But here's the thing. The interstellar dust problem isn't about our current technological limitations, it's about physics and arithmetic. The kinetic energy of a dust grain at 10% light speed is what it is, determined by E equals half mv squared. No future technology changes that equation. The density of the interstellar medium is what it is, determined by observations. The impact rate is what it is, determined by geometry. You can develop better materials, more efficient power sources, cleverer shielding designs. These might move the goalposts, might make the problems somewhat more tractable, but they don't eliminate the fundamental challenge. You're trying to move a fragile spacecraft containing delicate humans through an environment that's incredibly hostile at the required velocities. It's possible that some breakthrough could change the equation, perhaps some exotic physics we don't yet understand that allows faster than light travel without going through the intervening space, avoiding the dust problem entirely. But that's speculation piled on speculation. With known physics, the interstellar dust problem appears genuinely formidable, perhaps insurmountable for crewed missions. And here's another sobering thought. If this problem is as severe as it appears, it might explain part of the Fermi paradox, the puzzle of why we don't see evidence of alien civilizations. If interstellar travel is this difficult, if the dust problem dooms most attempts at crewed missions, then maybe civilizations arise on countless worlds throughout the galaxy but remain confined to their home star systems, unable to spread or colonize or make their presence obvious on galactic scales. We might live in a galaxy full of isolated civilizations, each trapped in their own solar system by the same fundamental barrier we face: the impossibility of shielding against interstellar dust at the velocities required for practical travel. Each civilization can see other star systems through telescopes, can even detect the presence of other civilizations through their electromagnetic emissions or atmospheric spectroscopy, but can never visit, never make direct contact, forever separated by distances that are traversable in principle but unsurvivable in practice. This is a lonely picture of the galaxy, not empty, but fragmented, with intelligence marooned on countless isolated worlds, able to observe the cosmos but unable to explore it physically. But wait, before I end on complete pessimism, let me explore one more class of possibilities. What if we change our definition of crewed mission? What if we expand our concept of human to include forms that can better survive the interstellar environment? In part 3, I want to explore the possibility of radically modifying humans through genetic engineering, cybernetic enhancement, or complete transformation into non-biological forms to create beings that could survive interstellar journeys that would kill unmodified humans. Because maybe the solution to the interstellar dust problem isn't better spacecraft, maybe it's better travelers. So we've established that the interstellar dust problem might make conventional crewed missions impossible, and that technological solutions within known physics all have severe limitations. Now I want to explore a more radical possibility. What if the solution isn't better spacecraft engineering, but fundamental changes to what we mean by human space travelers? What if we modify ourselves biologically, technologically, or informationally to create beings that can survive conditions that would kill baseline humans? This gets into speculative territory, but it's worth exploring because it might be the only realistic path to having any form of human-derived intelligence actually travel between stars. Let me walk through several approaches from least to most radical. First, consider biological modification through genetic engineering or other biotechnologies. Could we create humans or post-human descendants who are more resilient to the hazards of interstellar travel? The specific challenge of interstellar dust impacts is hard to address biologically because it's not primarily a biological problem. It's a problem of kinetic energy and physical destruction. No amount of genetic modification will make human flesh resistant to impacts carrying the energy of explosives. You can't evolve or engineer biology to survive being hit by what is essentially a continuous stream of tiny bombs. However, biological modification could address other challenges of interstellar travel that compound the dust problem. For instance, radiation resistance. Genetically engineered humans with enhanced DNA repair mechanisms, redundant genetic codes, or cellular adaptations from extremophile organisms could better survive the radiation environment of interstellar space. This doesn't help with dust impacts directly, but it means you could potentially use less massive shielding, which makes the spacecraft lighter and easier to accelerate. Extended lifespan. If the dust problem forces you to travel at slower speeds, perhaps 1 to 5% of light speed, to keep impact energies manageable, your journey might take centuries or millennia. Radical life extension through genetic engineering, cellular regeneration, or other biotechnologies could allow individual humans to survive journeys that would span many baseline human lifetimes. Reduced metabolic needs. Humans that require less food, water, and oxygen could travel on spacecraft with smaller, lighter life support systems. This reduces mass, makes acceleration easier, and reduces the size of the spacecraft's cross-section, potentially reducing impact rates. Hibernation capabilities. Some animals can hibernate or enter torpor states for extended periods with reduced metabolic activity. If humans could be engineered to enter similar states, perhaps for years or decades at a time, you could have travelers spend most of the journey in suspended animation, reducing life support needs and subjective journey time. These modifications could help. At the margins, they make interstellar travel somewhat less impossible by reducing certain constraints, but they don't solve the fundamental dust problem. A genetically modified human with extended lifespan and radiation resistance is still made of flesh and blood, still requires a spacecraft to travel in, and that spacecraft still faces the same impact hazard that unmodified humans do. So biological modification alone probably isn't sufficient. Let's consider more radical changes. Second, cybernetic enhancement combining biological humans with technological components. The idea here is to replace vulnerable biological parts with more robust mechanical or electronic alternatives, creating cyborg travelers who can better withstand the rigors of interstellar travel. In principle, you could replace many biological systems with technological equivalents. Replace organs with mechanical versions that don't require food or oxygen, reducing life support needs. Replace limbs with robotic versions, more resistant to radiation and impacts. Enhance the brain with computer interfaces that allow digital backups, redundancy, or the ability to transfer consciousness between bodies. Encase the remaining biological components in protective shells or distribute them redundantly throughout the spacecraft. A heavily cybernetic human might be much more resilient than a biological one. They might require less massive life support, might survive radiation doses that would kill biological humans, might even survive limited damage from impacts if their critical components are sufficiently hardened and redundant. But again, there are limits. Even the most advanced cybernetic systems we can imagine are still made of matter, metal, silicon, polymers that can be destroyed by sufficient kinetic energy. A dust grain impact at 10% light speed doesn't care whether it's hitting flesh or titanium. It releases hundreds of thousands of joules of energy in either case, vaporizing material and creating shock waves. You can harden cybernetic components, make them more compact and redundant, but you can't make them invulnerable. And the humans, or post-humans, still need to travel in a spacecraft that provides basic protection, power, propulsion, and communication. That spacecraft still faces the fundamental dust problem. Moreover, heavily cybernetic beings raise profound questions about identity and continuity. If you replace someone's organs, limbs, and eventually most of their brain with artificial components, at what point are they no longer the same person? At what point do they stop being human in any meaningful sense? This might not be a practical objection. Future civilizations might have different concepts of identity, but it's worth noting that sending humans to other star systems might turn into sending things that were once human but are now mostly machine. So cybernetic enhancement could help, but probably isn't sufficient on its own. Let's go further. Third, complete transfer of human consciousness into non-biological substrates, mind-uploading digital consciousness, whatever term you prefer. If we could scan a human brain at sufficient resolution and create a digital simulation that preserves the person's memories, personality, and conscious experience, we could transfer human minds into computational hardware that's much more resilient than biological bodies. A digital human, a mind running on computer hardware, could potentially survive conditions that would kill biological humans. The hardware could be radiation hardened, the data could be stored redundantly across multiple systems, backups could be maintained so that even if some hardware is destroyed, the consciousness can be restored. More importantly, digital minds don't need life support in the biological sense. They need power and cooling, but they don't need air, water, food, pressurized environments, or gravity. This potentially allows much lighter spacecraft, which helps with the acceleration problem. Digital minds could also tolerate longer journeys. If your subjective experience is determined by computation rate, you could slow down the simulation during transit experiencing days subjectively while centuries pass objectively. Or you could shut down entirely during boring transit phases and restart upon arrival. This helps with the psychological challenges of multi-century journeys. But, and this is crucial, mind uploading doesn't solve the dust impact problem either. Digital minds still run on physical hardware processors, memory, storage, power supplies, cooling systems. All of this is made of matter that can be destroyed by kinetic impacts. You can make the hardware more compact and redundant than a biological human, certainly. You might fit a digital consciousness into a much smaller package than a human body, reducing cross-sectional area and impact probability. You can maintain multiple backup copies so that if some hardware is destroyed, the mind persists, but you still need the hardware to function. A sufficiently energetic impact will destroy processors, corrupt memory, sever connections. If impacts are frequent enough or energetic enough, even highly redundant digital minds might suffer gradual degradation, bits of memory lost, processing capacity reduced, eventually catastrophic failure, as critical systems are damaged beyond recovery. Moreover, mind uploading, if it's even possible, raises even more profound questions about identity and continuity than cybernetic enhancement. Is the digital copy really you, or is it a copy that thinks it's you while the original you dies? If you create multiple copies, which one is the real you? These are philosophical puzzles that might not have clear answers. And there's a practical question. What does a digital consciousness do when it arrives at another star system? It can observe, collect data, transmit information back to Earth, but it can't build physical infrastructure, can't establish colonies, can't interact with the physical world in the way biological humans can unless you also send manufacturing systems that can build bodies or robots for the digital minds to inhabit. And those manufacturing systems add mass, complexity, and more vulnerable components that can be damaged by dust impacts. So mind uploading might be more feasible than sending biological humans, but it's still constrained by the fundamental problem that any physical substrate, biological or digital, can be destroyed by sufficient kinetic energy, and the interstellar medium delivers that energy relentlessly at relativistic speeds. Now let me consider the most extreme possibility, abandoning physical form entirely and existing as information patterns that can be transmitted as electromagnetic signals. Imagine encoding a human consciousness, all the information that makes you as data that can be transmitted via laser or radio waves to another star system. The information travels at light speed, experiences no dust, impacts because photons have no mass and can't be stopped by dust grains, and arrives intact, assuming the signal is strong enough and properly coded to survive noise and interference. At the destination, the information is received and used to instantiate a copy of the original consciousness in whatever computational substrate exists there. This could be receivers and computers sent ahead by robotic probes, or it could even be infrastructure built by an earlier wave of digital colonization, or in the most extreme scenarios, it could be receivers built by entirely different civilizations. This approach has some genuine advantages. Information transmission at light speed is as fast as anything can travel. There's no acceleration problem, you just turn on the laser or transmitter. There's no dust impact problem for the transmission itself. You can send the same information multiple times via different routes or frequencies to ensure it gets through despite any interference. You can send many copies cheaply, but the problems are severe and fundamental. First, this requires having